Physics, part 220. We've got an example for you. This displacement x at a time t of a particle moving in a simple harmonic motion is given by x is equal to 0.25 cos 7.5 t, where x is in meters and t is in seconds. A. Use the equation to find the amplitude, frequency and the period of the motion. B. Find the displacement when t is equal to 0.50 second. A. Compare the equation with x is equal to x0 cos w into t. The amplitude is x0 0.25 meter. The angular frequency w is 7.5 radians. Remember that w is equal to 2 pi f, so the frequency of f is equal to w over 2 pi is equal to 7.52 divided by 2 pi. 1.2 hertz. The period t is equal to 1 over f is equal to 1 over 1.2 is equal to 0.84 seconds. B. Substitute t is equal to 0.50 second in the equation. Remember that the angle wt is in radians and not in degrees, so w2 is equal to 7.5 into 0.50 is equal to 3.75 radians is equal to 215 degrees. So x is equal to 0.25 cos 215 degrees is equal to minus 0.20 meter. Now it's your turn. A mass oscillating on a spring has an amplitude of 0.10 meter and a period of 2.0 second. Deduce the equation for the displacement x if timing starts at the instant when the mass has its maximum displacement. Calculate the time interval from t0 before the displacement 0.08 meter. Now we get to the next section, examples of simple harmonic motion. By defining an object whose acceleration is proportional to the displacement from both equilibrium position and which is always directed towards the equilibrium position is undergoing simple harmonic motion. We now look at two simple examples of oscillatory motion which approximate to the definition. They may easily be set up by demonstrations of SHM. Mass on helical spring. Mass on a helical spring. The figure illustrates a mass m suspended from a spring. This sort of a spring is called helical spring because it has the shape of helix. The weight mg of the mass is balanced by the tension T in the spring. When the spring is extended by an amount of delta x, as in figure, there is an additional upward force in the spring given by F is equal to minus k delta x, where k is a constant for a particular spring known as the spring constant. The spring constant is a measure of the stiffness of the spring. A stiff spring has a large value of k, which is a more flexible spring has a smaller value of k, and for the same force would have a large extension than one with a large spring constant. The spring constant k is given by the expression k is equal to f over delta x, and it is measured in newtons per meter, Newton per meter. When the mass is released, the restoring force F pulls the mass towards the equilibrium position. The minus sign in the expression for F shows the direction of this force. The restoring force is proportional to the displacement. This means that the acceleration of the mass is proportional to the displacement from the equilibrium position and is directed towards the equilibrium position. This is the condition for simple harmonic motion. The full theory shows that for a mass suspended from a light spring having spring constant k, the period of t of the oscillation is given by T is equal to 2 pi under root m over k.